we are entering the last phase in the course, which is graphs. This course has a lot of overlap with 3080, but there are some differences in the way I will ask you to do things. So make sure that you're paying attention to that. And if you have any questions, be sure to ask. There will be some differences in the way I ask you to do, for instance, shortest paths algorithm, and perhaps a few other things. So what's a graph? A graph is a tuple VE consisting of a non-empty set of vertices. So you must have at least one vertex to have a graph. But the set of edges E can in fact be empty. And obviously edges connect two different vertices from V, and those are known as the endpoints of the edges. So the number of vertices is cardinality of V. The number of edges is cardinality of capital E. So capital V and capital E are the sets of vertices and edges respectively. A directed graph, also called a digraph, is defined as above, but it has the added constraint that each edge flows from one vertex to another. So the edges are not bidirectional, which is to say that VI, VJ, that edge, does not necessarily equal VJ, VI. So the above definitions also don't take into account vertices that have multiple edges between them. Such graphs are called multigraphs, and we will not deal with that in this course. Additionally, pseudographs are multigraphs that allow edges that connect vertices to themselves. This is also known as loops, and we will not deal with those types of graphs in 3110 either. So if we look at an edge VW, so V and W are endpoints, then endpoint W is said to be adjacent to V if such an edge exists. If the graph is undirected, then we say that V is also adjacent to W because that edge can be traversed and traveled in either direction. And an edge that connects two vertices is said to be incident with or to both of those vertices. So the degree of a vertex V, shown as deg of V, is the number of edges incident with V. And we may sometimes break this down into in degree and out degree and have sets for those, separate sets for those. Okay, so in some graphs, there is a value associated with each edge, and this is these are known as weights or costs. And we will use those in this class, and they'll be especially helpful when we try to do shortest path algorithms and the like. Okay, and so a graph with weighted edges is known as a weighted graph. A path in a graph is a sequence of vertices, W1, W2, W2, all the way to Wn, such that for all Wi, Wi plus 1, they're elements of the edge set. In other words, running through the edge set, we can find a path connecting those individual components. So the path's length is the number of edges that compose the path. And a cycle in a directed graph is a path of length at least 1, such that basically two nodes are the same node. Okay, so W1 equals to Wn. And a directed graph without cycle is called a directed acyclic graph, also known as a DAG. Okay, Now, how do we represent graphs in computation? There are a couple of primary methods. So first of all, we have the adjacency matrix representation, which is a two-dimensional matrix, cardinality of V by cardinality of V. And again, you'll remember that those are the number of vertices. And the rows and columns are indexed from 0 to n minus 1. And then each row represents vertices that are adjacent to a particular vertex, with an entry in column J if VI, comma VJ is an element of the edge set, okay? Meaning there is an edge where VI is one endpoint and VJ is the other endpoint. Okay, and the entry in this case is either going to be a 1, and that just simply indicates or can indicate just the existence of an edge, and it's a 0 otherwise, or it can be some value, usually a floating point value, representing the edge's weight or cost. An adjacency list, on the other hand, is an array with only cardinality of V, linked lists, and then at any location for any index I in the array, there is a linked list that holds all the vertices that are adjacent to vertex VI. The density of the edges in a graph is what should drive whether you choose the matrix representation or whether you choose the adjacency list representation. If the if the edge set is sparse, then it's better to go with a list, because having a matrix would have too many zeroed out elements. But if it is dense, then it is better to use the n by n matrix. Now here is a graph, an undirected graph on the top left, and here is its representation in both adjacency matrix form and adjacency list form. So we see here that 0 is connected to vertex 0 is connected to vertices 1 and 4, and we see that that's the case here. Here's 0, it's connected to 1, and it's connected to 4, and they're either zeros elsewhere or there's infinity elsewhere. That depends on what your application is. Here's another example, is vertex 3 is connected to 2 and 1, and so we see here that vertex 3 is connected to vertex 1, and it's connected to vertex 2. Okay, and vertex 4 is connected to vertices 0, 1, and 2, and we see that that's the case here. Here's 4, 0, 1, and 2, and no connections to either itself or to vertex 3. That same graph can be represented in an adjacency list by just having each element in the array be the pointer to a linked list, and then simply adding the adjacent vertices as elements in that linked list. So here we see that 0 connects to 1 and connects to 4, and that's the same as the graph up here, 0 connecting to 1 and to 4. 2 connects to 3 and 4, okay, and that's what we have here as well. 4 connects to 0, 1, and 2. Here's 4, 0, 1, and 2. And so since these are undirected edges, they really could be traversed in both directions, and they can be looked at from both perspectives, both edges, both vertices being endpoints. Now here is an example of a directed graph. So in this case, you see that, for instance, while vertex 2 connects to vertex 4, and there's an edge between 3 and 2. That edge is a directed edge. So vertex 2 in this case only has one outgoing edge. And so you can see here that it's only adjacent to vertex 4. Okay. Same thing with 3. 3 is only adjacent to 2. Okay. 1 is only adjacent to 3 because the edges are directed, and it's only 2. Vertex 0, it has two outgoing edges, one to vertex 1 and one to vertex 4. And representing that graph as an adjacency list is pretty much the same method that we looked at previously, except we take the direction of the individual edges. And so here's 0 connecting to 1 and 4. Everything else just connects to a single vertex. There's 1 to 3. There's 2 to 4. There's 3 to 2. And there's 4 to 1. Now, graphs can be traversed, and we need algorithms to traverse graphs to ensure that we cover every vertex in the graph. And so the idea then is that we want to visit every vertex in the graph. This would be akin to a node in a tree. But unlike trees, graphs have cycles, and graphs have isolated vertices, components that are not connected to one another. And so we cannot use tree traversal methods. We must use graph traversal methods. And there are two primary graph traversal methods, and we will look at both of those.